Today we're going to be talking more about graphing, and again the relationship between the graph, the first derivative, and the second derivative, and all that information it tells us. So there's a funny little acronym. This is not something you have to have memorized. M2I2 acids, which stands for maximum, minimum, intercepts, inflection points, asymptotes, concavity, increasing, decreasing, and symmetry. So the bottom line is there's so much information we can get from the function, the first derivative, the second derivative. So we can tell about maximums and minimums either from the change in the derivative, so derivative increasing, decreasing, decreasing, increasing, or from the concavity if the critical point is 0, or if the derivative is 0. Intercepts are a huge help with graphing. So to find the Y-intercept, let x equal 0. Find the x-intercept, let y equal 0. Inflection point, we take the second derivative and look for a change in concavity. Asymptotes, vertical asymptotes are anything where the denominator is 0. For horizontal, we're looking at the degree of the numerator and denominator. So if the degree is bigger on the top than the bottom, then it goes to infinity. If it's bigger on the bottom, then we go to 0. And if they have the same degree, it's the ratio of the leading coefficients. Concavity, if the second derivative is positive, concave up, second derivative is negative, concave down. And then, of course, increasing and decreasing from the first derivative. And the next thing I want to add, and you can write this on your notes, I'm not really concerned about the x-axis, but for y-axis, that means it's an even function, which means f of negative x equals f of x. And for the around the origin, that means it's an odd function, which means f of negative x equals negative f of x. So which of these things can we get from f of x, f prime, and the second derivative? F of x, we can get the intercepts. We can figure out what the asymptotes are. And any symmetry, whether it's an even or odd function. The first derivative tells us if the graph is increasing, decreasing, or if there are any maximums or minimums. And then the second derivative, we can tell about concavity, whether the graph is concave up or concave down, and where there are any inflection points. Alright, so this next example, there is a lot of white space because we're going to analyze a lot of different things about this function in order to graph it. So just for your reference, here's what my notes end up looking like. So make room. So we're just going to do this by what we can get from f of x, f prime, and then from f double prime. Okay, so the first thing that we can get here is the intercepts. Okay, we're going to do that by plugging in 0 for x and 0 for y. So let's start with 0 for x. So that's going to be 0 over 0 squared minus 4, which is 0. So when x is 0, y is 0. So that's actually both our x-intercept and y-intercept is at the origin. Next, we're going to look at asymptotes. Okay, so for vertical, we are interested in what makes the denominator 0. So in this case, x squared minus 4 equals 0. Well, that's going to occur at x equals 2 and when x equals negative 2. For the horizontal, we're going to look at the limit as this goes to infinity. Okay, well, the degree is bigger on the bottom than the top, so this limit is 0. So we have a horizontal asymptote at y equals 0. So I'm gonna, as we populate this, kind of highlight the things that will eventually be features of our graph. So right now we know it goes through the point 0, 0. It has two vertical asymptotes at 2 and negative 2, and a horizontal at 0. The last thing that we can get from f of x is symmetry. So we're going to investigate f of negative x, which is going to give me a negative x over negative x squared minus 4. So we have negative x over x squared minus 4, which is the opposite of what we started with. So this is negative f of x, which means this is odd, which means this graph is symmetric to the origin. So again, this will be a feature of our graph, is that it's symmetric to the origin. So those are all the things that we can get from f of x. Now we're going to look at f prime of x. And I'm going to do this derivative on a separate sheet so that we're going to be able to see everything here. All right, so I'm going to do this derivative here, and then I'll transfer it over to the other page. So this one, to do the derivative, we are going to have to do the quotient rule. So we're going to have x prime times x squared minus 4 minus x squared minus 4 prime times x all over x squared minus 4 squared. So x prime is 1, so we have x squared minus 4 minus the derivative of x squared minus 4 is 2x times x. It's going to be a 2x squared so this ends up being a negative x squared minus 4 over x squared minus 4 squared. So we'll transfer that over to our other page. So for our first derivative, we found this, so negative x squared minus 4 over x squared minus 4 squared. So we're going to make some number lines. One for negative x squared minus 4, and one for x squared minus 4 squared. And that will tell us about what's happening with our derivative. So a negative x squared, so picture a parabola facing down that's moved down 4, is always going to be negative. This one, x squared plus 4, or x squared minus 4, is going to be 0 at 0, but for every other value, since we're squaring it, it's going to be positive, which means this derivative is 0 at 0, but for all other values, this graph is going to be going down. So this graph is always decreasing, except for at 0. Okay, since there's no change, this is decreasing to decreasing, that means this graph does not have any critical point. Well, it has one critical point, but it has no extrema. So no maximums or minimums. Next, we're going to look at the, highlight that, always decrease, second derivative. Again, I'm going to do that work on a separate sheet. You don't need to. You should do it here, but I'm going to do my work on a separate sheet. So our first derivative is here. Our second derivative, again, we're going to need to do the quotient rule. So we have the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So this is going to be a negative 2x times x squared minus 4 squared minus this derivative is going to be 2 x squared minus 4 times 2x for the derivative of the inside times negative x squared minus 4 all over x squared minus 4 to the fourth. Now we've got a lot of things to keep track of here. I have this term, this whole term, and this whole term. They all contain an x squared minus 4, so I can eliminate one from each of those. So the square just becomes 1, that one whole goes away, and that one becomes a 3. It just gives us less to work with here. Okay, so I'm going to distribute here. So we'll have a negative 2x cubed plus 8x. Okay, here I'm multiplying, I'm subtracting, and we've got a 2 times this, and this, times this, times that. So negative 2 times 2x times a negative x squared is going to be plus 4x cubed. And then negative 2 times 2x, so our negative 4x times a negative 4 gives me a plus 16x. All over x squared minus 4 cubed. So combined like terms, we have 2x cubed plus 24x over x squared minus 4 cubed. The last thing I'm going to do is factor out the common factor so that it's easier to do our number lines. So I'll pull out a 2x, which will leave me with x squared plus 12 over x squared minus 4 cubed. I'll now transfer that to the other sheet. All right, so here's our second derivative. We're going to do a number line for each of the factors. And then a number line for f double prime of x. All right, so let's look at our critical points. This one is going to be 0 at 0. This one is never 0. This one's going to be 0 at negative 2 and positive 2. So this first one goes from negative to positive. X squared plus 12 is always positive. This one, since we're cubing it, if the inside is negative, it's going to be negative. If the inside is positive, it's going to be positive. So if I plug in a number less than -2, that makes this bigger than 4. So it's going to be positive there. If I pick a number in between here, like 0, that's going to be negative, and then it's going to become positive again. So we're multiplying the top and then dividing. So we have a negative on top over a positive makes that negative, a negative on the top and a negative in the bottom, a positive in the top, a negative in the bottom, and a positive over a positive is positive. So the information we can get from this is going to be concave down, concave up, concave down, concave up. And I should have put x's here. So at 2 and -2, those are asymptotes. So those are undefined. So there is one inflection point. Where it switches concavity in here. So even though it switches concavity from here to here, because the function's undefined there, that is not an inflection point. So we do have an inflection point when x is equal to 0, and that's going to be something that will help us graph. This graph is going to be concave up between -2 and 0, and when x is greater than 2, it's going to be concave down when x is less than -2, and between 0 and 2. So all of this is useful information for our graph. So our last step is to graph from all of this information. So let's put this all together. So you can put your graph somewhere on the page. I just have this so we can focus on one thing at a time. So the first thing, we have an intercept at 0, 0. So I know my graph goes through the origin. We have a vertical asymptote at -2 and +2. And a horizontal at 0, which means at the ends of the graph it's going to be approaching 0, and a graph is going to be symmetric to the origin. The rest of this graph is always decreasing. So I'm going to look at the middle part first. If it's always decreasing, then it's going to have to go from positive infinity to negative infinity going through here. There's an inflection point at 0. And remember, it's concave up before we get to 0 and concave down afterwards. So it's going to be concave up and decreasing to that point. It's going to be concave down and decreasing past that. That also makes it symmetric to the origin. Over here, it's going to be concave up and decreasing. So the only way we can make that happen and approach 0 is going to look like that. In this area, it's concave down and decreasing. So that's going to look like that. Okay, on this next graph, we have 5x to the 2/3 minus x to the 5/3. So we're going to do a graph in the calculator. So we've got 5x to the 2/3 minus x to the 5/3. We'll just graph that on a standard window. There it comes down, bounces up and down. Alright, so we're going to copy that to the notes. So our graph has a maximum here, it crosses and it comes in like that, and then up and down. Okay, so we're going to do the analysis with the derivatives and then compare that to our graph. Okay, so now we're going to take the derivative. So just a simple power rule. We'll multiply 2/3 down, so we're going to have 10 thirds x, and then we subtract 1 from 2/3, which is going to be to the negative 1/3, minus 5/3 x to the, if we subtract 1, that would be 3/3, which leaves me with 2/3. So we are going to factor out the least power. Before I do that, and you don't need to write this down, I just want to illustrate what we're doing. If I had something like 2x squared plus x to the 5th, we could factor out the smallest thing, which would be the x squared, right? So we'd have an x squared, which would leave me with 2 plus, if I factor out an x squared here, that leaves me with x cubed. So what you're doing is you're subtracting that power. So to get the 3, we took 5, subtracted 2. Now here, my smallest power is x to the 1/3. I have a constant that I can pull out of 5/3. And we're going to pull out the smallest power, which is x to the 1/3. That leaves me with, in this term, just a 2. In this term, we've pulled out the 5/3, so we're going to have minus x to the power. Here what we do is we take 5 and we subtract 2. Here what I'm going to do is take 2/3 and subtract negative 1/3. So 2/3 minus negative 1/3 is 2/3 plus 1/3. So this actually ends up being to the first power, or just x. Now we're going to make a number line chart. So I'm going to make a number line chart for 5/3 x to the negative 1/3. And we'll make one for 2 minus x. This one is 0 at 0. This one is 0 at 2. And actually this one is the same as 5/3 x to the 1/3. So this is actually undefined at 0, which, looking at our graph, makes sense. There is no derivative there. It's a cusp. So for the derivative to be undefined there makes sense. So our derivative is undefined at 0, 0 at 2. Again, that matches our graph. So we'll do our analysis here. So x to the 1/3, if we plug in a negative number, it's going to be negative. If we plug in a positive number, it's going to be positive. This one is 0 at 2. If I pick a number less than 2, like 0, it's going to be positive. If I pick a number bigger than 2, we're going to get a negative value. So my derivative, we're going to have a negative, positive, negative. And again, looking at our graph, that matches. It's decreasing, then it's increasing, then it's decreasing. Okay, but now we're going to reinterpret that information from the number line chart. So from the number line, this is increasing from 0 to 2, and it is decreasing from x is less than 0 and when x is greater than 2. So are there any local maximums or minimums? So looking at our graph, it goes down, up, and down. So the original function was defined. So even though the derivative isn't defined here, it still is going to be a minimum because the original graph is continuous. This is going to be a maximum. So when x equals 0, we have a minimum. When x equals 2, we have a maximum. Okay, now we're going to do another derivative. Okay, so we're going to have a negative 10 ninths when we multiply the 10 and the negative 1/3, x to the, looking at my power, we're taking this, and I'm doing the derivative of this, not the multiplied version. To subtract 1 from negative 1/3, so that's going to be negative 4/3, and then we're going to have a minus 10 ninths, x, I subtract 1 from 2/3, gives me negative 1/3. I'm again going to factor out the biggest thing I can, which is going to be a negative 10 ninths, x to the negative 4/3, that's the smallest power. In this term, that leaves me with 1. In this term, we pulled out a negative 10 ninths, and then we pulled out a negative 4/3. So we're going to have a negative 1/3 minus a negative 4/3. So that's a negative 1/3 plus 4/3, which would be 3/3, which is just 1. We'll do a number line chart here for those. I'm going to rewrite this one. This is going to be negative 10. Here's what I'm going to do. I'm going to write this as negative 10 over x to the 4 over 3. 1 plus x. So I'm going to do a number line just for the negative 10. I'm going to do one for 1 over 9x to the 4/3. I'm going to have 1 for 1 plus x. And then finally 1 for our second derivative. Okay, this one's going to be 0 at 0. Undefined at 0. This one's going to be 0 at negative 1. 0x. So it is 0 at negative 1, undefined at 0, because the first derivative was undefined at 0, so the second derivative is undefined. Negative 10 is always negative. This x to the 4/3, with the 4 being on top, that means this is always going to be a positive value. Because you're raising it, you're cubing it and then raising it to the 4th power. So anything with an even numerator will always be positive. This one's going to go from negative to positive. So let's look at the concavity. So here we're going to have a negative times a positive times a negative. Okay, so that's going to give me a positive. Here we've got negative, positive, positive, which will be positive. And then here negative, positive, positive is also, sorry, this is negative, 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 which again matches our graph. If we look at the original graph, this is a little hard to see, but apparently it's concave up leading to negative 1, and then it's concave down the rest of the way. Now let's get that information from our line here. So this is concave up, concave down, squeezing in these little areas. All right, so this is concave up when x is less than negative 1. It is concave down between negative 1 and 0, and then when x is greater than 0, but not at 0 because this function is not defined. So is there an inflection point? Yep, right here when it switches from concave up to concave down. To justify our answer, f double prime of x switches signs. In the interest of not making this an hour-long video, this example is fairly simple. It doesn't show you a whole lot. It doesn't really add to anything we've done. So if you want to copy this one from the notes, do that. This one, I'm going to go ahead and do in class, or you can copy down into your notes. But this one, it takes a while, but I think this would be a good example to do in class. So I'll do this one in class or get it from the notes. Okay, and I'll finish off going through this last page. Okay, so this is an AP problem. So suppose a function f is continuous, has a continuous second derivative for all x. And we're given this information. F of 0 is 2, f prime of 0 is negative 3, f double prime is 0. And let a function g be that whole mess of stuff. Okay. So we're going to write the equation for the tangent line at x equals 0. So that means we need our point and our slope. So my point is 0, 2. My slope is going to be the derivative, which is going to be negative 3. So my equation will be y minus 2 equals negative 3 x minus 0. For B, is there sufficient information to determine whether or not the graph of f has an inflection point when x equals 0? We know that the second derivative is 0, so that makes it so it potentially is a point of inflection, but we don't have any other information, so we don't know if it switches signs. So we do not have enough information for this. So we don't know if f double prime switches signs, because that's what needs to happen in order for there to be a point of inflection. And just the fact that it equals 0 is not enough information. Okay, given that g of 0 is 4, write an equation for the tangent line of g where x is 0. So we have our point. Next thing we need is our slope. This function here is the derivative. So g prime of 0 is going to equal e to the negative 2 times 0. So that'll just be 0. 3f of 0 plus 2f prime of 0. So e to the 0 is just 1. So we're going to have 3 times f of 0 from the beginning information is 2. Plus 2 times f prime of 0 was negative 3. So we have 6 minus 6. So our derivative here is 0. So for the graph of the tangent line, or the equation of the tangent line, we're going to have y minus 4 equals 0, x minus 0, which is just going to be y equals 4, or you can leave it like that. In part D, it says show that g double prime of x is equal to e to the 2x and all that. So we are taking this derivative. So this is going to be a product where we're going to have the derivative of this times this plus the derivative of this times this, and then we're going to do a lot of simplifying to get it to this format. And this is something that AP will do, is they'll show you what it is so that you can answer the second part of the question even if you can't do the derivative. Because if you do the derivative wrong and then make a wrong conclusion based on that for the second part, how do they grade that? So they tell you what the derivative is, so you can still do this, but then they give you more points for showing that. So, product rule. So we're going to have the derivative of e to the 2x times all of that. Plus the derivative of all of that. Sorry, I was looking at the derivative. We're taking the derivative of that. Let's try that again. G double prime of x is equal to the derivative of e to the negative 2x times the original first derivative that prime times the e to the negative 2x. So the derivative of e to the negative 2x is going to be negative 2 e to the negative 2x. Okay, the derivative here, 3 times f of x will be 3f prime of x plus 2f double prime of x times e to the negative 2x. Okay, I'm going to distribute through this to this and this to all that. So we're going to have a negative 6 e to the negative 2x f of x minus a 4 e to the negative 2x f prime of x here plus 3 e to the negative 2x f prime of x plus 2 e to the negative 2x f double prime of x. So in my next step here, I'm going to factor the e to the negative 2x out of all of them. And we could have actually done that from the beginning, but we needed that negative 2 there. So I'm going to pull out the e to the negative 2x and look at what it leaves me. So here, I'm going to have a negative 6 f of x. We're going to have a negative 4 f prime and a 3 f prime, which gives me negative 1 f prime. And then we have the 2 f double prime. So again, we know what the answer is. We just have to arrive there. So the second part of this question says, does g have a local maximum at x equals 0? So we know the first derivative is 0, which makes it a critical point. So now we're going to plug in and find g double prime of 0. So that's going to be e to the 0, negative 6 f of 0 minus f prime of 0 plus 2 f double prime of 0. I'm going to space here. So e to the 0 is 1. So we're going to have negative 6 times f of 0 is 2. F prime of 0 is 0. No, f prime of 0 is negative 3. So minus negative 3. Plus 2 f double prime is 0. So we have a negative 12 plus a 3, which gives me a negative 9. So what does that tell me? It tells me that so there are two conditions that are met. We know that g prime of 0 is 0, and at that point it's concave down. So our graph looks like that. So yes, it does have a local maximum, because g prime of 0 is 0 and g double prime of 0 is less than 0. So that's the second derivative test. Okay, so we'll do these last two quickly. So if the graph of y equals x cubed plus ax squared plus bx minus 8 has a point of inflection at 2, 0, what is the value of b? So we're going to take the first derivative, and the second derivative. Okay, if there's a point of inflection, that means the second derivative is going to be 0 when x is 2. So negative 12 equals 2a, which means a is negative 6. So now that we have a, I can plug it back into the original equation using this point. So 0 is going to equal 2 cubed minus 6 2 squared plus b times 2 minus 8. So 0 equals 8 minus 24 plus 2b minus 8. So the 8's go away. So 24 equals 2b, which means b equals 12. All right, we're going to do one last one. So this function here says f is negative on 0, 6. So I drew this graph because there's 3 points we're interested, 6, 8, and 10. So 6, 8, 10. So it's negative before we get to 6 and then positive afterwards. It's increasing from 6 to 8, then it's decreasing, and it's concave down to 10 and then concave up afterwards. So it's going to be concave down, increasing until here, still concave down but decreasing. At 10 it's still decreasing but it's concave up. Okay, so which is the least numerical value? F prime of 0. We don't know what it is, but it's increasing there, so it's going to be positive. At 6, our derivative is positive. At 4, we're concave down, so that makes this number negative. F double prime of 10, the second derivative there, switches concavity, is going to be 0. And f double prime of 12, since it's concave up, is positive. So the least one is that.